what will happen on a problem like this is the same thing that might happen if I was just asking you to do the antiderivative. You wouldn't stop and go, oh, that's a quotient. I need to think about it differently. You might just look at it and go, oh, 1 over x squared, 1 over x cubed divided by 3. It doesn't work that way. Okay? We need to make sure that we have x to the n, not a quotient, not a product. We can have sums and differences, but just x to the n is really the goal we're looking for. So the first challenge on this problem is recognizing, hey, that quotient means I've got a negative exponent. 1 over x squared in x to the n format is x to the negative 2. Make a little note here. Need something like this. Not a quotient. There isn't a quotient rule per se in antiderivatives. There's a couple things we do with quotients to kind of work around them. Couple different things. There's lots of special rules for antiderivatives that you have to learn. Some antiderivatives you can only find if you look it up on a table. For our basic power and function ones, first thing we try to do is, can we rewrite it as just x to a power instead of a quotient, 1 over x to the power. But then, once we kind of navigate that aspect of it, the steps are the same as any other fundamental theorem problem. But the arithmetic's going to be a little bit more challenging because my antiderivative is going to be x to the negative 1 divided by negative 1 plus c. And that's going to be a little messy to work with. Okay? We don't always do well with negative exponents, even when we have a calculator. The fact that we've got the negative 1 that we're dividing by as well, you know, sometimes we just kind of assume certain things happen and that leads us down the wrong path. So x to the negative 1 over negative 1 plus c, yeah, that's going to be a little bit more challenging. I made this 2. Oh, okay. I changed it. All right. It's not the same as on my paper. Okay, so I'm not going to expect to get the same answer. That's all right. When I do big F of 2 minus big F of 1, okay, I'm going to have to make sure that I am really careful with that negative exponent stuff and dividing by the negative 1. So 2 to the negative 1 divided by negative 1 minus 1 to the negative 1 divided by negative 1. I am going to sort of shortcut my work a little bit. Instead of writing f of 2 and f of 1 out separately, I've gone ahead and set it up automatically into the subtraction, and I automatically just went ahead and dropped the c's. I'll make a little note here. C cancels out. Here. Now, it's a good idea to kind of slow yourself down on this and make sure you're getting everything done accurately. 2 to the negative 1 over negative 1 is negative 1/2. Okay, so 2 to the negative 1 over negative 1 is 1 over negative 1 times 2 to the first. And 2 to the first is 2. So 1 over negative 2. Or negative 1/2, or negative 0.5. There's my little line that I always end up grabbing. Usually about this time in the notes. When I get tired, we grab that, erase it. Okay. There we go. So 1 over negative 2. Okay. minus negative 1. 1 to the negative 1 over negative 1 is 1 over negative 1 times 1 to the first power. And if you keep all the negatives straight, the final answer in this case is 1/2. We're not always going to get whole numbers. We're not always going to get positive numbers. We're actually going to do one with a negative number in a minute. Yeah, we'll do that one. Okay. So obviously, not obviously, but biggest challenge on this one is watching for this. So seeing quotients, rewriting them with negative exponents if we don't have it already written with a negative exponent. Okay. Similar to, we have a root, we got to write it with a fractional exponent. Negative exponents and fractional exponents versus roots and quotients are going to be our friends. Okay. So, two other things that we worried about when we did areas with graphs and integrals were things that looked like this. If we had, actually I'm going to go ahead and do this, graph this on Desmos so it's a little prettier. All right. There we go. And I don't want to do that one. Okay. But let's do this one. Okay. Graphing calculator. Let's say I wanted to look at y equals negative 2x minus 3. Okay. So different shaped curve now, negative 2x, so a line going in the opposite direction, but that's fine. Okay. And let's say for that function, I wanted to take the integral from negative 3, which is right here, to positive 1, which is right here. Negative 3 to positive 1, f of x dx, and that's my f of x function. So negative 3 would come up and hit there, positive 1 would come up and hit there, and we would be looking at this triangle and this triangle. Okay. One of these triangles is above the x-axis, one of these triangles is below the x-axis. That means there's something to worry about here with positives and negatives. If I'm going from negative 3 to positive 1, which is forwards, or forward, then I would be expecting that when I would calculate this area and I would count it as positive because it was above the x-axis, and I would calculate this area as negative because it was below the x-axis, and then I would put them together. And so this would be a couple problems. It would be this triangle's area and this triangle's area, and putting them together and making sure counting this as positive and counting this as negative, and that would be how we would attack that problem. Okay. And if I got rid of some of my ink here and I kind of cleaned it up a little bit, right, and we could look at the triangles. Actually, this is a little tougher because I gave us a kind of a weird number. So we had like a 1.5 bottom. So like a 1.5 bottom and a 3 side. So this triangle would be 1/2, 1.5 times 3. And then this triangle would be 1/2. And this is 2.5 across. And 5 down. And like I said, we'd count that as positive and that as negative, and that's how we would get that area. Isaac Newton actually makes it a lot easier for us. When we use the fundamental theorem of calculus, we do not have to worry about, well, is something going to be positive or negative? Because the fundamental theorem, as long as I follow the rules of the fundamental theorem will make it work for me. This looks like, if we were just going to guess, because I'm too lazy, this positive triangle is smaller than this negative triangle. So this answer is probably going to be negative. A big negative triangle, a littler positive triangle here. So what's this? This is like 2.25, and that's like 6.25. So I think we're gonna get -4. We'll see. We'll see how well I did that. I may not have done that well. I think we're gonna get -4. Definitely a bigger triangle here than here. But let's let Isaac Newton help us. All right. So Isaac Newton says, okay, you want to do the area between -2x minus 3 from is that what we had? -3 to 1? I went off script. Yeah, -3 to 1. If I want to FTC this, I can do it. I don't need to know what this looks like. I don't need to know positive versus negative. The positiveness and negativeness will work its way out through the fundamental theorem. This is what makes the fundamental theorem awesome, is it takes away a lot of the other thinking. All right, so big F of x is -2x squared over 2 minus 3x plus c, which I would definitely clean up into -x squared minus 3x plus c. Oops. Crazy lady. Okay. Definitely not going to work if I put a -1 up there instead. I'll get a totally different answer. Now, when I say you got to follow the rules of FTC, it's f of b minus f of a. Always, always f of b minus f of a. So big F of 1 is what we have to do first. Big F of -3 is what we do second, and then we subtract them. All right, so -1 squared minus 3 times 1. Don't really need the c. How about -4? You got to watch this. This is really tricky because it's an x squared and then make it negative. So 1 squared, make it negative, and then 3 times 1, subtract that. So -4 plus c. Oh, good Lord. All right, -3 squared minus 3 times -3 is, oh, how cool is that? -9 plus 9 is 0. Who said the answer was going to be -4? I got it. F of b minus f of a. F of b minus f of a. C's cancel out. and you get that it's a negative area. Ooh, and I'm making a mess. What was that? Oh, that was my phone. Gosh, that's like the second time I've done that. I'm amazed this phone still works. I always get it tangled in my thing. Nobody ever calls me. Oops. I hope I just didn't dial somebody. Let's exit. Okay. At least it was that phone and not my phone. Okay. So, yeah, sure, go ahead. Fundamental theorem, we don't have to worry about if something is supposed to be negative or positive. If it's supposed to come out as a negative answer, if the geometry would have it come out to be a negative answer, it'll come out as a negative answer using fundamental theorem as long as you do f of b minus f of a. Okay? So pieces above or below the x-axis, we don't have to worry about that. Okay. Now, if you were wondering, you're like, okay, well, you don't have to worry about that. Do I have to worry about going backwards? No. If we get a backwards problem, we can straight up do that problem backwards. Don't even really worry. When we're doing fundamental theorem, we literally don't really even worry about forwards or backwards. We just do the problem the way it looks. Let me find my last one. Okay, so this one, I went with let's do just x plus 3. Actually, let's not do x plus 3. I lied. Let's do x squared plus 3. Okay. X squared plus 3. May as well go rogue. And I'm going to do 0 and 2 for my limits of integration. But the integral is going to look like that, which would mean in geometry, in the graph problems, I'd have to go backwards. And if I have to go backwards, everything works backwards, and so that should be negative. We should, as we calculate that area, we should get a negative number. Okay. I don't have to know that ahead of time when I use fundamental theorem. I don't have to predict that. I don't have to look at it. I don't have to think about it. Newton has that all built in for us. And so if we're going to do the integral from 2 to 0, like that, of x squared plus 3 dx, no worries. This is b, this is a. We are still going to end up doing f of b minus f of a. If we stick to the theorem, the signs work themselves out. And so I think that's why Mr. Walters and I always disagree on this. He's like, every time you have it different, you should change it. I disagree. I don't think we need to change it here because it's not going to, we can get the right answer. If you flip this, you'll get a positive answer. If you flip this, you're supposed to put an extra negative in front. That will make your answer negative. You don't have to flip it. You don't have to worry about this as long as you follow fundamental theorem. Fundamental theorem will give you the negative result that you should get on this problem. Now, the interesting thing is a Riemann can't really take into account above and below the x-axis. Riemanns always think about going in the positive direction. So that is a little, actually, I don't know if any of I just said that, and now I'm wondering if that's true. I'm wondering if any of the applets, I'm not going to look at that right now. I wonder if any of the applets have that built in. They might. They may have already built that in. So, but we don't have to worry about it. Okay. So there's big F of x. Okay. And then We'll start with big F of 0 because that's the B value that's on the top. And the nice thing is a lot of the time when you're plugging in zeros, you're just going to get a 0. Or technically 0 plus C. But we're going to ignore the C. Oops, capital F. 2 cubed over 3 minus, plus 3 times 2 is 8/3 plus 6, which will be something like 18 and 8, carry the 1, 26 thirds. So how about 0 minus 26 thirds, or negative 26 thirds, or negative something, 8 and 2/3, or a negative 8.6. Maybe I'll look and see, will that applet do it? Find that applet. I can't do this one myself with geometry. I mean, I could. I just have to do like a lot of calculations. Let's do not Rihanna, applet. Let's see what this guy's look like. Yeah. All right. I don't know if I can use his, but I'll try. Here, let me throw it over here on my screen for a minute so I can play around with it. So f of x, well, let me type it. Okay. So what did we do? X squared plus 3 plus 3. And I don't know what all these other things are. But we're going from 0 to 2. I don't know how to use his applet. All right, don't know how to use his applet. Not working for me. Not good enough. Where'd that other one go? Nope, I don't like yours. It's too hard for somebody that's not super smart. This one's interesting. Let me try this one. All right, and can I change it from... Oh, I can do that. From 0 to 2. All right, so yeah, this guy's applet is not going to let me switch it, but we can look at the different estimations. Right hand, left hand, midpoint, trapezoidal. Oh, look how fun that is. Oh, I'm down with that. And as you increase the number of intervals, you can see that they're slowly converging on what we found to be the true answer. 8.67. Will it let me change that? No. So it's not allowing me to make it think about it backwards. So this, perfect, even in this applet, we would have to, knowing that we weren't doing the integral from 0 to 2, we were doing the integral from 2 to 0, that this would be backwards. But at least the number tends to go. What's lower? These are two other. Let me see what that looks like. I don't know those two. I have no idea what that means. Okay. All right, so not Riemann problems, fundamental theorem problems. Fundamental theorem problems are all the same in some ways. Find the antiderivative, plug it B into it, plug A into it, subtract, you get your number. They can be different. You can have negative exponents, you can get negative answers, you can plug negative numbers in, all of those things can happen, but the overall attack is still the same. So, what I'm going to ask